It's my honor to introduce Dr. Xu Liu. So he's from NASA Langley. So most of you already saw his long CV, right? So he got his PhD in 1989. So to me, even that is pretty long ago. So that's how senior he is. But most interesting, he's so active. He's so active. I think that's where you will gain today, right? So in his long CV, I don't want to go over this, but the key thing is that if you're working on NASA, biggest thing confirmation how good you are is that you win NASA big awards, right? So he won NASA Exceptional Scientific Achievement Medal in 2022, right? That's 2 years ago. That's indicating his contribution. But for those know, right, remote sensing and the radiation, so we have fancy instruments. We got a lot of data now. The challenge is how we can effectively use them, right? And use it to study climate. He will tell us a lot today, right? So then you take over.
Okay. Thank you. Well, first of all, I would like to thank you all for inviting me to come over here, and so nice to see young students. I'm the older generation. So basically, I'm going to talk about radiative transfer modeling and the retrieval algorithm development. Even though I'm the speaker, there are a lot of people behind this work. So we have a group of 9 people at NASA Langley, and also with collaborations of NOAA, universities, and even with European partners. So here's the outline of my presentation. Anyway, I will give you an introduction of satellite remote sensing in general, because this is a university environment. I would like to give you kind of an overview of what NASA satellites programs are. And then I'll talk about the challenges in radio transfer modeling of dealing with satellite data. Steve was just talking about that. So it's because as the satellite get more advanced, we have a lot of spectral channels. It's very difficult to modeling those. So I will show you how we deal with that, which basically is this PCRTM work. Doesn't seem to be okay. So it's called principal component-based radio transfer model. And then I'll talk about how it's applied to satellite remote sensing data. And then how is this full model is used for inversion algorithms to retrieve properties from satellite data. And finally, I'll give you a conclusion. So here's the a chart from the NASA website. So basically, give you a timeline of the current and future Earth satellite missions. So you can see, well, we have EOS period back in the 80s and the early 90s. So you can see, I just want to say that we have active remote sensors, we have passive remote sensors, and we have high spatial resolution remote sensors and high spectral resolution sensors. So for example, one thing I want to say is the hyperspectral sensor become more and more popular because it gives you more information. I just want to point out, like on Aqua, we have TESS. It's a hyperspectral infrared sensor that has like tens of thousands of spectral channels. In the past, in the 80s, 90s, so the satellite remote sensor, if you have a dozen spectral channels, that's great. And we suddenly jump from dozens to thousands or tens of thousands. So that brings big challenge to the satellite remote sensing. And then the Aqua, the Terra, where's the Terra? Terra. I mean the Aura, TESS is on Aura. The AIRS is called atmospheric infrared sounder. It's on Aqua. And then we have the SNPP. We have CrIS, ARMS, and the SNPP is followed by the JPSS-1. It's hard to read here. By JPSS-1, and we have JPSS-2, 3, and 4. So right now we have 2 JPSS on orbit. It's every 5 to 7 years. So we'll have this for decades to come. And then so those they have hyperspectral sensors on that. They are a lot. a lot like EMIT is hyperspectral sensor in the solar spectral region. Tempo just launched last year hyperspectral sensors. And then we have microwave sensors and infrared sensors. Okay, so the microwave sensor has the simplicity that it doesn't have a lot of trace gases interfering in the main sounding channels. So you have like operating lines, and then you have water vapor lines. The retrieval is a little bit straightforward, but the microwave sensors has a lot of big antennas. It put a lot of constraints on the size. And the other advantage of microwave is it can penetrate. It doesn't see pretty much the ice cloud, except if it's precipitating cloud. For the water cloud, it only has absorption, so it's easy to model. So microwave remote sensor is good for atmospheric sounding, but not sensitive to ice cloud, but it can penetrate the cloud below the cloud. Okay, that's why the GPS it can penetrate even precipitation if you go to even shorter, longer wavelengths. Okay, so the infrared hyperspectral sounder it has a lot of trace gas absorptions. You can have like tens of trace gas that are actively having spectral features there. So not only you can retrieve trace gases, but also using like the CO2 lines or water lines, you can do atmospheric temperature sounding. Okay, so the advantage of infrared is it gives you more information, but but also sensitive to both ice and water cloud. So when the optical depth gets larger, like optical depth equals to 4. Pretty much you don't see anything below the cloud, so it has limitations on that side. But if you have relatively clear sky or partially cloudy sky, you can do atmospheric sounding all the way to the surface. Okay, and then you have solar instruments. Here I don't want to point it out of them. There are a lot of solar instruments. Okay, so the solar instruments can see through the cloud maybe more. You can get optical depths up to like 50 because of the amount of multiple scattering of the clouds. Okay, so but it's radio transfer wise, it's a lot more challenging because you have to account for the inhomogeneous scattering of the solar light during the day. And then the active sensor, which is very active in this university, is very good with spatial resolution. You can have high spatial resolution and vertical resolution. So, and you can do, temperature, water vapor, aerosol clouds, and the trace gases. It's pretty diverse. But if the laser technology is developed enough, we can put in the space. That would be great. We have Calypso and EarthCare that have all the cloud passive remote sensor. So anyway, I just want to give you a very rough explanation there. Now, so for you have the satellite measurement, then you want to do the retrieval of atmospheric properties like temperature, water vapor, clouds, trace gases, surface properties. You need a radio transfer modeling because the radio transfer model can simulate what your satellite observed. So until you can do that, you cannot do any retrieval. Okay, you can do AI retrieval, have some partial truths, and then you do this AI linking between observation and the truth, which is not global training. Okay, so the best way is really physical retrieval. You have this fully understanding what you're measuring, and then you can, based on radio transfer, you can invert the properties. As I said, so when the hyperspectral has tens of thousands or thousands of spectral channels, it's very computationally challenging. First of all, to properly account for atmospheric trace gas absorptions in the solar and the thermal infrared spectral region, pretty much in the relatively broad region, you need millions of radio transfer calculations in order to resolve the Doppler half-width of the line, which are mostly due to the upper atmosphere, where the atmosphere are thin, so the thermal motion kind of dominates the spectral line broadening. So in the lower atmosphere, it's more Lorentz line broadening, as you can tell from the radio transfer theory or remote sensing books. So anyway, so 2 million radio transfer calculation are too time demanding. There's no way you can use that for satellite remote sensing applications. So what people do is, okay, if in the old days I have 2 dozens of spectral channels, okay, you have a filter type of a spectral response function, I can just do one radial transfer calculation for each spectral channel. So I only do like 10 or 20 radial transfer modeling, which is affordable. And now when you suddenly go to thousands of spectral channels, this is not going to work. Okay, so plus to parameterize those are channel-based radial transfer modeling, there are a lot of assumptions made which may not be accurate. So anyway, we kind of to deal with hyperspectral remote sensing applications at NASA Langley, we developed this called principal component-based radial transfer model, which will satisfy the requirement of speeding and accuracy. I will show you later on. So basically, if you read the radial transfer model book, you can see there are different, like the band model is very old ones, like the Cooley's old book. Older models, they're using kind of a band model. Limited accuracy, not accurate for multiple gases. And then, of course, the narrow network. In the old days, the narrow network was not popular, and although people are using that for that, but there are some limitations, like how accurate is Jacobian, the weighting function calculation, and it's not physical parameterization. I think for forward model nowadays, I think it's okay. You can train your model as long as your reference training model is accurate. You should be able to use AI to satisfy this requirement. Okay. And then for the correlated K and this exponential sum fitting, if you have a broadband, so you kind of smartly rank your absorption coefficient according to its magnitude. So all those millions of spectral lines become a smooth function. And then you can use, kind of pick different spectrum, different regions and do an integral, using like, let's say, Gauss quadrature or whatever way to approximate what within that spectral channel, how I can calculate the effective impact. But the problem is the atmosphere is inhomogeneous. Okay, as you go from the surface with high pressure, go to lower, the spectral line shape are changing. So when you try to convert that into smooth curve, at each level, that curve changes. But people don't know how to handle that. They do all kinds of assumptions, correlated K, assuming they're perfectly correlated. And then the trace gas, you have to do that separately for trace gas and for different species. And once you convolve your monochromatic radiance with an instant function, the BS law doesn't apply. You cannot just multiply two transmittance together to form a total transmittance, because it's like you do integral first, or you do the integral first and then you do the product, versus you do the product within the integral and then you integrate it. Those are two different concepts. Okay. So there are a lot of approximations in the correlated K and the exponential sum fitting. So in the past, like 3 decades, people have been trying to find all kinds of solutions to kind of alleviate these fundamental flaws. So still in the climate community, this is heavily used because it's easy to generate this kind of coefficients. But it's not good enough for satellite remote sensing applications. And then the RTTOG is a European fast radial transfer model. The CRTM is a US side. So it's kind of using kind of an effective transmittance for each layer. So it forces the BS law to be valid. But they are kind of a non-physical parameterization. So the problem is it's hard to increase the accuracy because it's ad hocly try to predict the effective transmittance for each layer in atmosphere. So it's hard to get the accuracy right. But most importantly, if you add other things to it, you have to retrain your effective transmittance, which is not that good. And then there's optimal spectral sampling. So all those radial transfer model, we'll call it channel-based. Okay, they do radial transfer one channel at a time. So if you have thousands of spectral channels, I still need to do thousands of radial transfer calculations. So the PCRTM is the one that kind of jumped this kind of a constraint. I don't have to do thousands of radial transfer calculations. I can do a few hundred, and yet I can get the spectral channel radiance very accurately. So that's basically the essence of it. So how does that work? Okay, so you have channel radiance for each spectral channel radiance. I should say that for one spectral with thousands of spectral channels, okay, you can decompose that into different eigenvectors. Okay, you have a sample of data you can decompose into, like 1,000 eigenvectors. But since the eigenvectors are orthogonal to each other, so they represent the information content very compactly. So instead of using thousands of eigenvectors, maybe I only need a couple of hundred to represent the whole information content of your hyperspectral data. So that's the key. So using the PCA to compress the spectral into a few hundred elements. Now the next question is, how do I model those few hundred eigenvector or the projection coefficient? Okay, so giving me a measurement, I do a projection onto those eigenvectors. I end up with magnitude of those projections. Those magnitudes, a few hundred magnitude, we call projection coefficients. They are capturing all the essential information of your original measurement. So if you want to convert back to the original channel spectral, you just multiply that weight by the eigenvector, you will get the original measurements. Okay, so it's very accurate. So this PCRTM find a way to predict that projection coefficient in this way is called C. It turned out it's proportional to the monochromatic radiance. Okay, but you have millions of monochromatic radiances. Most of them are redundant. So we'll find a way to remove all the redundancies. Only pick the essential information that can accurately predict or calculate the C, the projection coefficient. So basically, that's the instance of the principal component based radiative transfer model. Okay, even though the PCA is a kind of conceptual mathematical phenomenon, but the radiative transfer is very physical. Okay, because I'm doing monochromatic radiative transfer calculation at a few hundred selected wavelengths that can effectively represent you see as accurately as I want relative to the line by lines in my training process. So it turned out, so in the here give you an example. Okay, the PCRTM, we have a NAST-I hyperspectral. So we have 8,000 spectral channel. With PCRTM, I only need 300 to 900 monochromatic calculations. So for each spectral channel, is you need less than 0.1 radiative transfer calculation per channel. Now with channel based, you need at least 8,000 spectral channel calculation. For the OSS, it needs even a lot more. So you can see the number of predictors for each channel. They are dramatically different between channel-based versus the principal component-based radiative transfer modeling. So here is an example of showing you, like this is oxygen A band in the solar spectral region. So you have a lot of spectral lines with high spectral resolution. But we can just pick about 7 monochromatic frequencies that can represent the whole spectral information. I can regenerate each of these lines by linearly combine these 7 points, and then we basically calculate the PC scores, which is here, PC scores. Okay, so we get the PC scores. And the PC scores, we'll use it for the retrieval too. But if you want to get the channel radiance, you just do a EOF transformation, because you just use the magnitude combined with the eigenvector, you will get the channel spectral. Okay. So this is just to show you that we have applied this principal component radiative transfer model to a lot of satellite and airborne sensors with spectral channel ranging from over 1,000 spectral channel all the way to 20,000 spectral channel. And if we just stay in the PC domain or eigenvector domain, we only need 5 milliseconds to calculate one spectral. So it's tremendous improvement in speed relative to other models. Now, if you go from 1,000 spectral channel to 20,000, we jump from 5 milliseconds to 14 milliseconds. So it's not proportional to the number of spectral channels. In other words, it's trying to tell you that even though your resolution increases dramatically, your information content may not increase that much. Okay. So the PCA method, it correctly select the essential monochromatic frequencies to represent those information. Oh, okay. So since we're talking about satellite remote sensing, I just want to say this is a weighting function for the thermal infrared spectral region. So we have water lines here, we have CO2 lines here. So this CO2 line, the two CO2 lines, they are used for atmospheric temperature sounding. Okay. So this weighting function is the top of atmospheric radiance with respect to the temperature at each layer in the atmosphere. So in this case, we have like 100 atmospheric layers. So you can see the CO2, those lines are sounding the upper atmospheric temperature. Okay, as the frequency goes, you can see it start to kind of sound. This is atmosphere surface atmosphere pressure. So it's 1,000 to 0 here. So this is basically what we call the CO2 slicing, the principle of temperature sounding. Okay, in the old days, they assume CO2 is uniformly mixed, it doesn't change. But nowadays, we try to retrieve it. But anyway, so as you pick different channels, it has different sensitivity at different height. Okay, so that's basically the principle of atmospheric temperature sounding. Of course, you have a lot of phase gases and this water vapor you can use for that. So we have extended this method to the solar spectral region. This is just to show you this frequency grid is gone. But anyway, this is about from 300 nanometer to 2.5 micron. Okay. This is the real SCIAMACHY measurement. Is a European satellite that has been decommissioned. But you can see the measurement agrees with our simulation very well. And I forgot to mention, for the solar, this is an AISI instrument that's launched by the UMASat. They have 3 copies of this satellite there. So and they're going to do the AISI next generation, which is 7 years apart for next 3 copies. So this will be like 40 years of data record from this. So we can simulate the spectrum very well. The CrIS, as I mentioned, is SNPP, J1, J2, J3, J4. Each one lasts 5 to 7 years. So we have, again, 40 years of data record if, talking about in the future. So we can simulate the spectrum very well. This is AIRS. That's the one on top of our Aqua satellite. It has been there for 20 years already. So it's trying to deorbit. It's reaching its lifetime. The satellite is reaching its lifetime. So it's starting to drift orbit. The instrument is still working. So anyway, this is just to show you that not only we did that for the SCIAMACHY, we did that for Tempo. Tempo is another satellite that was launched last year by NASA. It's different from other polar orbiting satellite. Okay, the polar orbiting satellite is visiting the Earth. Depends on the angle of inclination. Maybe once or twice a day. Well, basically twice a day. Okay. But for the GEO, since it's on the high, from let's say 700 to 800 kilometer height orbit to GEO, sun kind of a geostationary. It's Earth synchronous orbit. So you can look at the US or some other part of Earth constantly. So you can do the diurnal observation. Okay, so that's the difference. So with Tempo launch on the geostationary satellite, it puts a lot of computational burdens because you have so much data to look at. So with the PCRTM is developed for kind of OMI at that time, but eventually we're going to extend that to Tempo. OMI is another satellite by European UMASat. Okay, so the other application of the PCRTM we have a Claro Pathfinder project at NASA Langley. Okay, it's a hyperspectral sensors that covers the spectral range from 350 nanometers to 2.5 microns with hyperspectral resolution. The difference between this one and the previous satellites, like the MODIS or VIIRS, is for the solar instrument, it's very difficult to do the calibration. So like VIIRS or MODIS, they are solar instrument with multi-spectral. Okay, like 3 dozens of spectral channels. the calibration accuracy is on the order of 2 to 4%. With Claro Pathfinder, the calibration accuracy is 0.3%. So there's an order of magnitude improvement in the calibration. So hopefully this instrument will be launched in a couple of years. This will be a big impact on the solar measurements. Okay. So at Langley, we are developing algorithms for inter-satellite calibration and also doing the RC type of thing. So we simulate the spectral, we retrieve it and see how this satellite performs atmospheric, retrievals, things like that. Okay, so in order to do that, we need to simulate high, kind of a spatial resolution image. So with PCRTM, we took the MODIS level 1 data, put it into PCRTM, calculate the radiance, and then compare with the observed one. Okay, the observed one is a broadband, and here we are hyperspectral. So we only pick, a few channels and compare with the observed one. You can see the two agrees with each other very well. So based on this simulated hyperspectral data, we can do a lot of things. We can do inter-satellite calibration. We can characterize the spectral shift. We can do the band extension because we want to calibrate the SIRIS instrument, which is a total radiation budget instrument, which has a very broad spectral coverage. But the CPF has limited spectral coverage. And we have, using PCRTM, we have developed an algorithm to match the two using the hyperspectral information. So this is just another example of using PCRTM to simulate the VIIRS observation. So you can see the simulated and observed one agree with each other pretty well. This is the one that we did for the EMIT. EMIT is a satellite that was launched, I think it was 3 years ago on International Space Station. It's a hyperspectral imager with very high spatial resolution. It's 60 meters. Okay, so you get hyperspectral, but also you get high spatial resolution. So you have huge amount of data. There's a big impact. So in the past, they were using like a Martran to do this radio transfer modeling. There are a few deep problems with that. They try to generate lookup table, but Martran is not fast enough to generate a global lookup table. So they have to do it for one scene at a time. Then you have a lot of scenes each day. So that itself is taking a lot of time. So we developed a PCRTM for this instrument. So we can simulate the global lookup table in 2 hours. So if we were to use the old methodology, it would take hundreds of CPU, few years of time. Most importantly, you cannot afford the power, to do that kind of calculation for that many years. It's just economically not possible. So just to give you the flavor, the speed of the full model. So again, the PCRTM. So we take the EMIT level 2 data, we'll put it into PCRTM, we simulate the radiance. So you can see the two kind of agree with each other pretty well. There are some disagreement at some wavelengths. That is known because the instrument has like a grating overlapping region. They have the straight line that has some artifacts there. So you can see this goes from about, I think it's 280 to 2.5 microns. Okay. So anyway, you have the spectral feature. Now, if you just pick one wavelength and this is measured, so you can see the high spatial resolution. I think it has 1.6 million pixels. So you can see the simulated versus the observed. They agree with each other very well. This 2.2 microns, and this is 6.5 microns. So you can see they have different features from the top of atmosphere, but the two agrees pretty well. Now, if we do the RTP image, that includes all the wavelengths, and again, the observed one versus the simulated one agrees with each other very well. Just to show you the high fidelity of this full model. Now I'm going to switch to the retrieval side. Okay, so for the retrieval side, as I said, you want to do a physical retrieval algorithm. So you want to use really transfer modeling to relate what the satellite observed versus what you want to retrieve. So what affects the TOA radiance? Think about it. So it's what is in the atmosphere. The water vapor is the major one. You have all the trace gases. Of course, you have cloud, ice cloud and water cloud. You have aerosols. And then on the surface, you have surface reflection, you have surface emission, you have surface temperature, and so on. So all this you have to take into account in the radio transfer modeling. Okay. So the physical retrieval is the best way, which we need a full model. But in the past, okay, for the hyperspectral infrared sounders, they cannot do the cloudy radio transfer modeling because computationally just impossible 20 years ago. So they end up with an algorithm called cloud clear it. So I want to remove the cloud from my observation, and then I can use clear sky radio transfer model to do that. And even with clear sky, they can only pick a few hundred channels out of thousands of spectral channels. So that's the old technology. So right now the NOAA operation algorithm, the NASA operational algorithms, they're all using this algorithm. Okay. The problem with this algorithm is you sacrifice your spatial resolution. So for CrIS and AIRS, so one field of regard has 9 field of view. Okay. They have to use 9 field of view to remove the cloud. And not only that, they have to have a very good first guess of your quote unquote clear sky radiance. And they cannot do that until they bring in the NWP model or using a good neural network thing that trained on an NWP model. So the problem with that is the NWP model, most of the time, 90% of the time is very good. But when you have frontal situations, you have features, it could be, you can forecast the thing, but it's in a different location. You have phase errors, okay? So in that case, you know, you're training towards a wrong, you're constraining your solution to the wrong place. So the cloud clear radiance will be biased. So anyway, and then there's an algorithm called physical retrieval based on all sky. So nowadays we can do radio transfer on the cloudy sky. So there are different algorithms for doing that. But I think the PCRTM, we call it a single field of view atmospheric product, is the Langley, NASA Langley developed one. This is the only one that uses the climatology. We do not use NWP model as any a priori. We retrieve every single field of view. Most importantly, we use all spectral channels. All other algorithms, they are picking few hundred, like 1 or 200 spectral channels out of thousands of spectral channels. So, and then of course there are statistical method. Okay, you can do linear regression. So if you know with radio transfer model, okay, you know the TOA radiance, top of atmosphere radiance, you know the atmosphere temperature water vapor. I can do a regression based on the radiance measurement and get the temperature water vapor. Okay, so there are 2 issues with that. One is it's not a linear problem. Radio transfer equation is highly nonlinear. So the regression will not work globally. So what people do is they have to stratify the atmosphere into different conditions. So by doing that, your retrieval may have some stratification. So the statistical method, the advantage is no matter what, I'm going to get a solution. But how good it is when the real situation, the TOA radiance, deviates from your radio transfer model. That's the thing. So there's no radiometric consistency of your product versus what is observed by the satellite. So that's the danger of the statistical method. The same thing with AI. So there are 2 issues with AI. A lot of things, like I said, they will rely on so-called truths, in situ measurement, aircraft measurement, sound, and then they relate that to the atmosphere radiance. Those training data are very limited, and if you apply to the global scene, it could be biased. And then you use the radio transfer as a training. If your radio transfer is not accurate, then when you apply to the real data, there are differences in the thing. Again, you will get beautiful results. You get coherent results. but that result may not reflect quantitatively. It may not reflect the real quantity you're observing. So really, we want the key thing is whatever your product you're retrieving, it should be consistent with what you observe. So in the SiFSAP algorithm, we guarantees that we fit the observed radiance directly. And then we develop another method called spectral fingerprinting method. Okay, we also kind of satisfies that. So this method is almost like a statistical method, but we use our SiFSAP physical retrieval as our training data. Okay, so by doing that, it's very fast, but we ensure the radiometric closure. Okay, so I guess I don't have time to go into the details, but anyway, so just want to show you some results. So we have this SiFSAP, single field of view physical retrieval algorithm. We have a spectral fingerprinting method called ClimFiSP. Okay, so the SiFSAP again is it has a 3 times higher spatial resolution. Actually, it should be 9 times the area spatial resolution. We use all the spectral channels and so on. And the key thing is we're retrieving everything simultaneously. The temperature, cloud, water vapor, trace gases, surface emissivity, surface skin temperature. So our product are very consistent with the satellite observation. And the other important factor of this is, excuse me, is that you have a complete suite of the atmosphere and surface product. So if I have a radiative transfer model, I can put into radiative transfer model, I can calculate the TOA flux, surface flux, I can calculate heating rate, cooling rate at each level. So it's very significant with this kind of self-consistent product because you will be relating to both weather and the climate studies. So this is the water vapor 3-dimensional. So this is a long track. This is cross track. So cross track we have about 2,000 kilometers. So a long track, it's about 14 kilometers spatial resolution. And they keep moving. So I don't know the movie has played, but you can see we can capture all the variations of the water vapor. Now this one is from our climate product, the ClimFiSP. So this is a 20 years of the AIRS CrIS measurement. And we process all the data, we get the anomaly, and then we derive the trend from it. So again, because the ClimFiSP is almost like a machine learning based algorithm, it's very fast. So we can process 20 years of data very quickly. Now with the current operational product from the NASA DAX, they will take the level 1 data and then do the processing to level 2, which is very time consuming, and then average level 2 into the Earth grid, form the level 3 product. Okay, so that's very, very time consuming. So even if my radiance calibration has improved or my radiative transfer modeling has improved, you will make a big decision to reprocess the data. Like no one will not reprocess the data. NASA may reprocess, but it's a big effort. So with this kind of algorithm, I can reprocess the data very easily because computationally it's very efficient. So if you have a new finding in level 1 data or your algorithm has improved, I can quickly reprocess it. But most importantly is the methodology that with multiple satellite, I only need my SiFSAP trained for 1 satellite. Everything will be, we have a radiative kernel, which is equivalent to weighting function. We apply the same thing to all the satellite sensors. So in other words, we try to eliminate the error introduced by the retrieval algorithm, or not the error, the inconsistency between different satellite instruments. Okay, so this has a very big significance. Now for the level 1 to level 2 algorithm, you have no algorithm, you have NASA. NASA has different algorithms as well. And then European have their own algorithms. So if you lump them together to form level 3 and do a trend, it's is not going to be good for climate data record. Okay, so you have to do a lot of tuning. And now, as I said before, some of the operational product they use NWP as a priori. So like it turned out, you can see that NWP has a lot of information on ozone. You can see beautiful ozone maps each day. But when you try to do a trend, you can see the steps, okay? Because the NWP, the data assimilation community is taking the historic data, right? In the past, the ozone was from SBUV, from other sensors, and then they switched to OMI, which is higher spectral resolution one. So they have dramatic improvement in the ozone quality. So the retrieval, the level 2 algorithm are different. So you can see a jump there. And then they have different versions of a level 2 algorithm. So when they jump from version 2 to version 4, you can see another discontinuity. So by doing that, you cannot get a trend out of that because those discontinuity will overwhelm your small climate signal. Hey, anyway, so let me move forward on the retrieval algorithm details. So as I said, the CrIS, AIRS, and the IASI, they have 2,000 to maybe 8,000 spectral channels. So if you do an inversion, well, first of all, radio transfer model to include all the channels is computational too expensive. But if we compress it into PC domain, that's the number of PCs we use in our retrieval. Okay, so you can see it's an order of magnitude reduction. But the information content of all these PCs really contains all these spectral channels. Now, on the retrieval side, we retrieve a lot of properties. We have temperature at 101 level. We have water vapor, CO2, ozone, and all those trace gases at 101 levels. So and then we have surface emissivity at a lot of wavelengths. And in this case, we have a few hundred wavelengths. And then we'll have cloud properties. So if you lump all this together, the state vector, the retrieve parameter will be 1,000, over 1,000. And this is a tremendously air-conditioned inversion problem. We cannot do that. Computationally, it's not efficient either. So we follow the same principle. We compress this retrieve parameter into the principal component domain. So you can see we reduce the dimensionality dramatically. The number of eigenvector or PCs we choose depends on the information content. For example, we don't have a lot of information for NO2, N2O and methane and CO. So we have a much less eigenvectors. And this number can be changed. Okay, depends on the instrument. I can change this number up and down. Depends on the information content. This is just to give you a flavor of how the eigenvector looks like. So this is atmospheric pressure from, let's say, this is 1,000 hectopascal to 100. So, in the troposphere. So you can see this is first eigenvector, second eigenvector, and so on. So as you go to higher eigenvectors, you're capturing the fine structure. Okay. So if your information content is higher, then you can use more orders of the numbers of eigenvectors. So in the optimal estimation retrieval, the averaging kernel is very important concept. Okay. So the retrieval algorithm, the inversion will give you an equation that give you a retrieved product error covariance matrix, but also will give you averaging kernel. So the averaging kernel, so this is the pressure, this is the magnitude of averaging kernel. This is the sum of all this averaging kernel for particular pressure level. Okay. So the magnitude tells you how much information is from the measurement. Okay. And if it's large, that means it comes from measurement. If it's small, it comes from the a priori. And then the half width of this averaging kernel tells you the vertical resolution of your product. Okay. So this is and then the summation of the two of all this together, if they are close to 1, that means all your information comes from the measurement, from your retrieval, not from a priori. Now for the water vapor, this is for temperature. For the water vapor, you can see most of them are close to 1, but here it's not exactly 1. So that means some information are from a priori, so you have less information in the upper atmosphere. So just to give you a flavor of, let's say this is the current NASA operational CO product. As I said, it has the average 9 field of view, but this is the SiFSAP, our retrieval product. So with the increased spatial resolution, you can see we can this is Australia file. We can see the CO features very well. Very high coherency and a very fine vertical structure. With this cloud clearing, we're not seeing that. Okay, and this is this is a thermal infrared product. This is a solar instrument. So the solar instrument is more sensitive to the cloud and the plume from the fire. So you can see there are a lot of gaps here because the cloud interferes with retrieval. So it has more kind of that. But the two agrees with each other pretty well. You can see those fine features. At the beginning, we thought it was just the artifact of retrieval, but it turned out they are really true features of the the CO plumes around over the ocean in Australia. So anyway, just to give you some, and then we have okay. So I better speed up. So we have like as I said, we have different copies of CrIS instrument on orbit. So some of them are flying like 40 minutes apart or 50 minutes, I forgot. So it's like flying in tandem. Okay, so same thing on the Earth, I observed it twice. So by monitoring the atmosphere, the image change, like the water profile change at different pressure level, we can derive the wind. Okay, so this is from the low resolution, the ClimFiSP product. So you can see the density is much lower. This is our product from the single field of view retrieval. Not only that, the bias is increased by a factor of 2 or 3, and so just to show you the importance of fitting the original radiance versus the cloud clear radiance. This is an example of showing you the convective cloud movement. So you have we have profile inside the convection or outside. Okay, it turned out inside the convection you have higher temperature, you have higher moisture because the convection is raising the hot air up in the atmosphere. So we can capture all that in our retrieval. The current like AIRS version 7, those cloud clearing algorithm, because they don't have enough spatial resolution. But most importantly, in the cloudy region, they rely on WP, which has lower spatial resolution. They are not capturing this. The cloud initiation are very small features. You come and go. I was talking to Dan about this cloud. This is very fine structure. So with single field view, this is very helpful. This is just to show you the consistency between the SiFSAP and ClimFiSP. The two agrees with each other. We also compare with E7WF profile. It agrees pretty well, except there are some. Well, basically overall, 99% agree well. This is the. Just want to say, we have AIRS, SMPP CrIS, JPS1 CrIS, 3 sensors flying in the same year. They are flying together. Okay, so anyway, just to see the retrieve temperature, they kind of overlap with each other, just to show you the consistency of the model. And then from that, we can derive the trend surface skin temperature. So this is an anomaly from temperature anomaly from 2002 to 2022 or 23. So looks noisy, but it's the signal, the anomaly. Okay, we remove the seasonal variation. So these are true variability from year to year, with month to month as well. So with that, we can derive the trend over 20 years. So this we have like I said, there are thousands of properties. Even we compress it into the information content, we still have over 100. A few hundred. So we can plot this kind of thing very easily for any parameters. So we are trying to do the application for that. This is just to show you, we'll do this daily, but this is just monthly mean to show you, like this is temperatures, in the 500 hectopascal is water vapor, the surface skin temperature. This is water vapor. Anyway, so you can see this kind of movement for monthly mean, but also daily product as well. This is just to show you that we have done AI retrieval based on our PCRTM training. This is the EMIT observed image. This is our retrieve cloud. It's very high accuracy in the sense that we capture all this, like you cannot see the cloud. So the current EMIT algorithm, they only see like patchy things to do the cloud mask, miss most of them. So anyway, so this is another example. So in summary, satellite remote sensing give you a lot of information, but radial transfer modeling is very challenging. So in order to do retrieval well, we need a good radial transfer model. And NASA Langley, since 2023, we have been developing this principal component-based radial transfer modeling, and it's being applied to far infrared, mid infrared, solar spectral region. We're going to move that into microwave spectral region as well. So anyway, that's all I need to say. So thank you for listening.
Thank you very much. A lot of information. Questions? Yeah, before I ask questions, so we will have lunch, right? So in a chance, challenge hall. After that, we have students have a chance to talk with Dr. Liu. So.
Yeah, and nice talk. And I have a basic question, or two basic questions, if I understand that correct. Your PCA approach works likely so well, if I can understand it right, because the radiances or the bands are so close. There are so many.
Exactly.
They even work better the more you have. At the end of the day, if you would have just a few which are far away, like one at 1,000 nanometer, one at 5,000, and so you may have much more difficulties. But because you have so many bands, therefore you can reduce it from 30,000 to 200. You have still a good representation.
Yes.
That's correct how I think about it.
Yeah, so there are two dimensions. One is spatial dimension you're talking about. The other is spectral dimension. So for us to represent the global scene, we try to simulate the radiance as diversified as we can. We sometimes even synthesize that it's not real. Like for the cloud, we put all kinds of clouds in our model, and the surface, we just use random number to generate surface. That's not realistic, but we capture all those. Now, when you talk about why we're reducing the number of eigenvectors, it's really the correlation, as you said. So you have, let's say, 8,000 spectral channels, but a lot of them are similar.
Yeah, that's the
So they are highly correlated. Therefore, by doing PCA, we compress all those into few eigenvectors.
I understand.
Yeah, that's
now comes a very basic question. We teach the students that the satellite signal the satellite retrieves is usually maximum at unit optical depths.
Okay.
And so how, and I was struggling when I see your data and the work, and you hinted to that at the end of it with the vertical resolution. And you have this transfer functions. And
Yeah.
I still don't 100% understand that.
Okay.
So what? Sometimes you reach unit optical depth maybe in 100 meters, but sometimes you may need 2 kilometers or so.
Yes.
How do you circumvent that, or how do you use that data, or how do? Well, I try to understand.
Yeah. I think all those questions are very fundamental and essential. It's a great question. So basically it depends on the information content, right? So for example, the up-looking instrument that look at the sun, they can have very high spectral resolution. So they can resolve the Doppler broadening and the Lorentz broadening. And the Lorentz broadening is mainly the higher the pressure. So by retrieving, fitting that whole thing, they know where to put the gases in the atmosphere. That's the theory based on that. But the resolution is very limited. It's scale height, basically like 5 to 7 kilometer vertical resolution. Now with limb sounding, you have satellite looking at the sun, but the sun is moving, satellite is there, right? So basically, you slicing the atmosphere very one layer at a time. So the vertical resolution is very high. You can be hundreds of meters or 1 kilometer typically. but the horizontal path length is long, because you will see hundreds of or thousands of kilometers, in the atmosphere. Okay, so and then so all the average current will tell you that for the limb, the average current is like a delta function, very sharp. Okay, that's the beauty of this thing. And then for the thermal infrared, because it's so sensitive to the emission in atmosphere. Okay, so like you said, this optical depth equals to 1. That's exactly the principle of the CO2 slicing. So we have a strong CO2 lines. Okay, in the center of the CO2 absorption, they get saturated in the top of atmosphere. Little bit of CO2 saturated. So that spectral channel is centered in the upper atmosphere. So the temperature of that upper atmosphere temperature is very critical to that channel. But that channel does not see anything below it because the optical depth becomes, tens or hundreds. So that channel is opaque to the surface. And then you go to another, CO2 line. There are more, yeah. So that's the principle of the thermal infrared sounding. It really, where it gets optimal 1 optical depth. A different channel has different strengths, okay, absorption strengths, and therefore they peak at different height. Okay.
That's beautifully elegant.
Yeah, remote sensing is very interesting, very powerful, but you have to really understand the essence of it rather than just, I'm grabbing some other people algorithm and go with it. I think it's this kind of question, I think is so important. So thank you for asking that question. I think it's beautiful.
So one more question, then we can move to the launch. Yeah.
Yeah, my observation in some way similar to Daniel's, just a very nice presentation, very nice treatment of so much data. I think the key word you used in your talk, and Daniel also alluded to it, is redundant. There is so much redundant information that you are able to get rid of a lot and end up with confidence in the product that you produce. So it's very encouraging.
Yes.
My question has to do with surface retrieval and wavelength dependence of surface reflectivity. I don't know how much attention you pay to that, but one of the great interests in surface retrieval is chlorophyll. And are you able to in some way produce a chlorophyll map as a function of time and location so that we can better get a handle ultimately on something like photosynthesis rate? Yeah,
that's a good question. So yes, so our radiative transfer model deals with ocean surface. So surface reflection over ocean depends on the wind speed as well as your angle. We have foam, in fact, we have different mirror facet, but also depends on the chloroform and also this the sedum and other compounds. So we do have model to model those kind of things. So I'm not personally doing real satellite measurements, but actually we do. We have the RSP, the GES polarimeter that fly on aircraft. So we are retrieving the sedum, the chlorophyll concentration that. But it's aircraft field mission related. Now the PACE mission, the PACE is a satellite that was just launched, I think last year, at the end of last year, is specifically designed to measure the chlorophyll on the global map. So in the past, they were using CWIF and maybe some of the MODIS product to derive that. But now they have a specific hyperspectral sensor that measures the chlorophyll and the other algae.
On terrestrial.
On terrestrial, yeah. They do have that. The thing in the lake.
That would be a real game changer.
Yes, yeah. The preliminary product should be available at the NASA Goddard already. But I forgot to mention the SiFSAP product is also available at NASA Goddard, so we can claim this is operational product as well. So hopefully more people will use the SiFSAP our product. But we are trying to move towards the solar spectra and do more retrieval. So a lot of potential there.
Thank you.
Okay, let's thanks Dr. Liu one more time, so then we move on. Okay.